Hello, my name is Professor Brothers, and this is going to be a short video on simulating the project for ECE 3872. So first thing that I want to do is look at the example proposal, and in this there is a schedule. The schedule calls out CDR in week 6 of the class. Prior to CDR, you must have a simulation completed. I wanted to give you a head start on that simulation and give you some examples of what it should be. First off, we're going to start by looking at some Tinkercad projects that I've created I'm going to share with you. The first one, it has the Arduino drop-down. It has a little breadboard, and you can drop down LEDs and switches and speaker and a volume control and tempo. So all these things can be dropped down on this breadboard. I'm going to provide you with a copy of this Tinkercad so you can play with it. But the most important thing about this is a project that I'm calling the Conductor. The most important thing about this is here is the code for the Conductor. This is the code that is going to play row, row, row your boat, and this is the code that your project will be tested against. So I'm providing this to you so you can have a stimulus for your project and be able to go over it. There are two versions of the Conductor that I put out here. This is the first one, and the second one actually has a motor and a servo connected to it. And so this one is simulating the interaction with the electromechanical interface. You can start these simulations and run them in the web interface, but keep in mind it doesn't run real time. So the song is a little bit choppy. So that's the first thing that you can look at for examples on the simulation. The second thing, here is a Matlab simulation. And in this Matlab simulation, I've set up a little simulated world with a sampling frequency of 40 kilohertz. And then I go through and I create a digital signal that is going to represent row, row, row your boat. In order to do that, there's this Conductor simulation, and in this Matlab, there's the exact same code that's found in Tinkercad. So I'm giving it to you in two ways. First is the C programming from Tinkercad. The second is a Matlab simulation, but both of them should be equivalent, should be the same. So if we come over here and run this Matlab, at the bottom, you can see my headings. I have some parameters are set up, and create the song given the input tempo, and then create the digital signal associated with that song. So I'm going through and creating the sine wave. Then I replicate that. So the digital, what I'm calling digital, is a pure reference of the song Row, Row, Row Your Boat. I create this other version called signal, and then I shift it a little bit to simulate a time delay. I do some plotting, and then I'm going to do envelope detection. I'm going to find the tempo, and then I'm going to sync the time. When I run this, it will first give the tempo as set, and then the tempo as measured. Now notice, it's taking a moment to actually produce the answer, and the measured time offset is going to be 0.0013. This is seconds, when the actual time offset was 0.0015 seconds. And here are some plots. Here's the actual envelope, and then here's the spectrum of the envelope. And if you look towards the bottom left, you can see here are the harmonics. So there's the primary harmonic, there's the DC offset, the primary harmonic, and then all the other harmonics. So the fundamental harmonic and all the other harmonics. Here is the envelope of the actual audio, and then here's the spectrum of the song, Row, Row, Row Your Boat. And you can put a marker on each one of these, and you'll see that these correspond to the megahertz of the musical notes. And then here's what it looks like. So each note is followed by a short resting period. So it is a little bit of music and a rest, music and a rest. I put these rest beats in there in order to give us something easy to synchronize the timing and the tempo on. So I'm going to provide this MATLAB code, but I'm not going to provide these functions at the bottom. This is what you need to develop. You need to figure out how you're going to synchronize the time. You're going to figure out how you need to synchronize the tempo. And this needs to be done, completed before CDR. You need to understand the algorithm that you're going to build into your robot before you really get into building the robot. You need to understand the algorithm. Now, notice one thing that I said about the time that it took to come up with the measured time offset values. We can also look at the variables that are over in this space. And you can see there are some pretty big variables. The Arduino processor, you must use the Arduino Uno. And in that, it has a very limited processor space. You also need to figure out what of these can you do in hardware and what ones do you want to do in software. So for instance, this is sampling at 40 kilohertz. So let's change this to 10. And then there's this thing that's down here. You can change the tempo. You can change the octave. But then there's this other parameter called tempo resolution. And if we set this to 0.5, 0.1, it goes too low. And so it'll actually throw an error in the MATLAB code. So don't go too low with this. And don't go too high. If you go to a value of 1, it'll lock up your computer. So if we go to something like 0.6, you can see it just gave us the answer very quickly. And we can see more of the spectrum. That's because it's decimating the signal more. So you need to go through this process and think about what do you actually need to have it sampling at. So let's set the sampling rate at 5 kilohertz and see what that does. We can see that it comes up even faster, but we can also see that the error between these two values is much greater. Okay? So you need to create a simulation. You need to have this simulation drive the design. And so this is going to be a circular process. You might pick out an analog to digital converter and say, okay, we're going to use this one. But then you get information from your simulation and say, actually, this isn't a good one to use. We might need to reselect this part. Then you check it with the simulation again, check it with the part. And so it is a circular process that one informs the other. This simulation is very important for the success of your project. All right, I think that that's everything that I wanted to cover in this tutorial. We'll see you in class.